Okay, today let's go ahead and try another one of these double artillery problems where we've got some particular projectile launcher. Maybe it's something used to trigger avalanches or something to clear out the snowy slopes. And it's being launched from some foot of this hill. The angle of inclination of the hill is, let's call it phi. And then we're launching the same speed, but we're going to launch at two different angles with respect to the horizontal. We'll call those alpha and beta. And we're hitting the same location on the hill. However, because of the different angles, they do take two different times to land there. And our goal is to determine the distance from our launch point to the impact location, and that I do mean along the hill's slope, in terms of the two times. So I don't want it to depend on V naught or on any of these angles. I want to know what is the distance just in terms of the two times. So it might seem like, boy, it should depend on all these things, but we're going to see that it actually does not. So what do we want to do here? Well, we want to write down our general trajectory equations for both of these. I'll leave t generic at first, and I'll just sort of have a generic launch angle theta also, and then we'll just sort of have two copies, one for theta equals alpha and t1, one for theta equals beta with t2. All right, so in the x direction, we know that this location over here is going to be v naught cosine theta times t, whichever theta of launch we have and whichever t for total time in the air we have. We also know that the y component will be v naught sine theta times t minus 1/2 gt squared. Okay. Seen those a million times. All right, now what I want to do is actually try to maybe eliminate these angles. I know it seems like we're given these two angles, but honestly, we're not really. I put those in as a placeholder, but they're not supposed to show up in our final answer. Only T1 and T2 should show up in our final L. So I want to try to get rid of them somehow. I do know what these are based on geometry also. The x component of this location, well, that's just going to be L times cosine phi. And the y component of this location is just going to be L times sine phi. So if I'm trying to get rid of some of these unknown angles, maybe I should divide by t in this first one, divide by t in this second one, and then sum the squares of the v naught cosine theta and the v naught sine theta. The reason for that is because I know sine squared plus cosine squared equals 1, so the theta bit will disappear entirely. There will be t's there, and t's are fine. I'm okay with having the t's. But I want to get rid of these thetas because I was not really told explicitly. I know it looks like it, but these are really not known values of these launch angles. So let's put that up here and see what happens. Okay, so for starters, divided by the t, I also moved this term over to make it a positive, and we only have a linear term there. Now I'm going to square both equations and sum them. Pretty common thing to do when we have an unknown angle variable that we want to get rid of. On the left-hand side, I'll have a v naught squared cosine squared plus v naught squared sine squared, which is v naught squared sine squared plus cosine squared, which is v naught squared. So goodbye theta, gone. On the right-hand side, well, it looks a little weird. We're going to have to write it out. So L squared cosine squared phi over t squared plus, this is a binomial squared, so I'm going to have to expand that out. I'll have an L squared sine squared phi over t squared. That's nice because we can see that phi is going to cancel as well. I have my cross term here, which will pick up a factor of 2 because it's doubled. That gets rid of that. And the t times the t also goes away. And then I've got this term here, which will be a quarter g squared t squared. And just to simplify one more time, these two can be added together to give me just L squared over t squared. Let's do one more little bit of simplification here. I don't like having this t squared in the denominator. It's a little irritating. So let's multiply the whole equation by t squared. And notice that what we're going to get is two copies, really. I'm going to have that equation for a generic t. But notice there's no thetas in here. Phi is the same number. It's fixed. It's the angle of the hill. L is fixed. G is fixed. V naught is fixed. So I'm just going to have an equation that's got a t in it, but t could be either t1 or t2. So I could use two copies, and then maybe by subtracting them, something nice will happen. So let's see what happens. I'll write down both copies. Remember, we're multiplying by t squared first. Okay, so here's the first version. Cleared out the denominators, and I'm plugging in t2 specifically. And then here's my second equation, again, plugging in t1. It's supposed to be true for both of these times. These are the same landing points. And now let's subtract these two from each other and see what happens. On the left-hand side, we're going to have a difference of squares. That sounds kind of nice. L squared minus L squared cancels. We'll have another difference of squares here. And a difference of fourth powers way down there. Okay, not too bad. In fact, if I divide by this difference of squares, I can see that these first two bits that'll cancel out. This difference of fourth powers is actually also a difference of squares. It's a difference of squared squareds. So I can factor this into the difference of squares that I'm trying to get rid of. Why are my exponents looking so bad today? The difference of squares that I'm trying to get rid of times the sum of the squares. And sure enough, dividing out this term, and this term, because, and that should be a 2 there, 2 minus 1, because we're assuming that t1 and t2 are not the same value, we end up with something very nice. Okay, so what we're going to do now is I'm going to bring this equation that's kind of mostly finished here up to the top, and we'll keep one of our equations here in order to try to eliminate this final phi term. Okay, so I brought them over here. This is the equation we just ended with. Notice that we have that cancellation of all those difference of squares, and that difference of quartics gave us the sum of squares. That's nice. And then I wrote down one copy of the line that was kind of just up around here. I chose the T1 version, although you could do the T2 version too. It wouldn't make any difference, because I now want to try to eliminate V naught squared from both of these equations. And the way we're going to do that is, well, literally just take this value, take this value, multiply by T1 squared, set it equal to this, and see what happens. So let's see what happens here. Taking everything that equals V naught squared and multiplying on the left by T1 gives us okay, that's the left-hand side of this lower equation. Then the right-hand side is just the right-hand side. And since I'm running out of room here, I'll go ahead and just put the next line down here. Okay, now we'll expand this out. The T1 squared I'll distribute to everything, and we'll get some nice cancellations. I will also expand this out. Okay, that's the left-hand side. Okay, a lot of expanding, but look what happens. This term and this term are the same. This term and this term are the same. I'm only left with an L right here, and everything here is a square. Oh, how nice is that? So the distance from our launch point to this point of common intersection can be written entirely in terms of just the 2 times. Notice that's it, which means this will hold for any slope angle, including, by the way, level ground. It does not depend on you knowing, although you could go calculate what these have to be, the alpha and beta, but it does not depend on you knowing what the launch angles are, either relative to the horizon or relative to the slope. It also does not depend on V naught. I mean, there will be a specific V naught to get there, but this answer doesn't depend on it. The T's themselves kind of implicitly depend on it, but if you just know the 2 T's, you can still measure that. I like that. That's really nice. Anyway, there it is, our launch distance purely in terms of the 2 times for these 2 different launch trajectories. Notice there really only are 2 different same initial speeds that will give you the same intersection point. So it's not like there could be a T3 or something. There are only 2 unique trajectories that will have the same start and end point for a fixed speed, but we've got that single value for L in terms of them. QED.